Hello, and I'm Jozsef Varga from Leiden Observatory, and I'm thanking for the opportunity to present this talk online in this nice conference. So the title is Harnessing the Full Power of the VLTI to Resolve Planet Formation. And before I start the talk, I want to follow up on the last talk by Benjamin, because so I'm part of the Matisse GTO, VLTI GTO team, and we were working on this object on AG 163296, and we published some results last year, which confirmed the time variability of this dust clump with Matisse. So we compared the Pioneer modeling results with the Matisse modeling results, and we saw that this asymmetry changed its location. But since we only had one epoch with Matisse, and also it was the year when one of the two gravity observations were made. So we could not measure the period. So and this is very nice that you were managed to do it, and independently from this work, we also planned a follow-up with Matisse to measure the period of the clump, and I just showing this animation which shows what will be the observables which we can measure with Matisse in L band at 3 micron if we observe this source. And we got the time, and we plan to do this observational sequence in this year. So maybe that will provide an independent confirmation of the orbital period that Benjamin measured. So just after this, I would like to present what I was about to talk about. Let me then I put this in full screen. So I would like to talk on the substructures of planet-forming disks and how VLTI can use to uncover these substructures. What are these substructures? So we can see spirals, we can see rings, we can even resolve the inner regions of the disks where the dust sublimates. Oops. And we have now amazing instruments for doing that. For example, Sphere on VLTI. Also, I can mention GPI. We have ALMA, and also we have VLTI and Chara. VLTI and Chara measure resolve these disks and much higher angular resolution, and also those are sensitive to the much inner parts. And that's the region that I'm interested in. And I would like to show some results for the young star HD 144432, which will show how can we use all VLTI instruments and combine all data from the different instruments to build a consistent model of the disk. So this object is a pre-transitional disk, which is very good because that is the exact object type where we expect that these interesting these structures are present in the region which we can probe, which is 0.1 to 10 AU scales. And the aims of this modeling is to describe the new VLTI Matisse data from the guaranteed time observations and also the SED information, and reveal the structures. And we also already have some nice results from Legend on this, where this was also based on interferometric data, and so this gap was already assumed to be there. Now, if we model these new Matisse data, what can we see? That I show here the visibility, and the model points are the crosses, data are the circles. As Matisse is a two-band instrument, that left is showing the L band, the right is in N band, and what we can see with a simple model, which is a Gaussian, that the N band, the disk looks bigger at longer wavelengths. But based on this modeling, we cannot tell anything about substructure, because this just shows that the disk emitting region differs, which can be true for structured disks and continuous disks as well. Now we want to connect these data sets, connect in a single model, and for that the temperature gradient model works very well, where we assume radial temperature distribution as a power law, and then this model predicts the disk, how the disk looks like at different wavelengths. So let's see this temperature gradient model for this data. Again, the circles are purple, circles are the data, and the crosses are the model, and the purple color refers to the 3 micron, the L band, and the red color refers to the N band data. You can see that in L band 3 micron, the model doesn't match the data. So this model, where we have a cavity inside, which assumed to be the dust free region inside the dust amylidation radius, doesn't work. Okay. Then the next step is, let's introduce a gap in this model, as was done by Legend et al. And what we can see here, that if we put the gap between around 0.4 and 0.9 AU, then the model works very well. So good, so far so good. But what about the spectral energy distribution? So this is the spectral energy distribution of the object in the infrared regime. So here the points are the data, and the yellow line is the model SCD. And what we can see, two things, that one is the mid-infrared silicate bands. This is a continuum model, so it's not modeled. But the other thing that we can see, that in the not the near infrared, but between 1 or 2 to 8 micron, the model gives too little flux compared to the data. And so it turns out that its model is not good. So how to proceed? What we learned so far is that the disk has substructure, a gap in the inner 1 AU, and the model gives too low flux in the 1.7 micron range. But the other important thing, that the infrared emission is optically thin. So based on this, simple blackbody models might not tell the truth. So the optical properties of the dust should be taken into account in this modeling. And so the next step in the modeling is to add more data. We added the Pioneer data and the gravity data. Thanks for that to the gravity team. And also included the dust opacities in the model. And this is the first model which we tried out, where the dust which we put in the model is composed of mainly silicates and carbon. And this is what is used in the Diana project. It can be regarded as a standard dust composition for protoplanetary disks. And what we can learn that it gives not bad fit, but it also doesn't feel it has some shortcomings. So here this plot on the top left shows the visibility with the baseline, effective baseline, and the different colors correspond to the different instruments. So the gray is Pioneer, the red is Gravity, the yellow is Matisse L-band, and the black is Matisse N-band. And where the fit is not good for the Pioneer, and also so fit is not very good for all of this shorter wavelength VLTI data. And
2 minutes left.
2 minutes left. Oh, yeah, that's perfect. Then also to the SED. It's not very bad either. But let's look at these dust opacities a bit. So in blue color, this is the Diana standard dust which we used in this in the previous model which I showed. We experimented with different dust compositions, including silicate, also silicate dust with a different grain size distribution. Also, we can experiment with amorphous carbon. And here is this red line, which is the opacity curve of the iron dust. And I would like to show this result. So the model with iron grains, and I argue that if we put in the inner disk part iron grains, while the outer disk part outside of the gap, we put silicates and carbon dust. So this Diana dust composition. Then it gives a very good fit to the data, and where there is this rim of the silicate rich disk at 0.6 AU. The only shortcoming that the peak of the silicate feature is too small in the model. And so here's my take-home message. So VLTI is a powerful tool to detect this substructure, and I showed how can we use the 3 VLTI instruments as one. And knowing that some or many of these disks which we investigate has a optically thin inter-disk emission, that we can use this VLTI data to get constraints on the dust composition and grain sizes. And this transitional disk HG14442 is an excellent laboratory for doing this. When there is a disk gap in the inner 1 AU, also it can be carved by a planet. And if we compare our model with a hydro simulation, then we can see some nice similarities. And also it might provide evidence for radically different dust properties in the different inner regions inside the gap, inside 0.6 AU, and outside of the gap. Thank you for your attention.
Thank you very much for the talk. Do we have any questions? Anything online? Or maybe I can start while people are typing. So just looking at the comparison here between the model and the hydro simulation, there seems to be some quite strong asymmetry in the hydro simulation. Do you see any evidence of that asymmetry in your models?
Yeah, we can see asymmetry in the N-band data, which probes this part outside of the gap. And also this we can see also time variability in the N-band data. In the shorter wavelength, the 3 micron and shorter, the asymmetry is much smaller, and also the time variability cannot really be estimated. based on the current data.
Thank you. We have a question in the room.
Hi, Jozsef. Thank you for the talk. I was wondering, do you have any idea what could cause this iron only at the center, not outside?
Yeah, that's a good question. No, I have no idea. It has to be investigated. So, what is that? But does filtering can do it? Because if we imagine that there is a gap, there is a planet in the gap, this can filter dust. So only the very small dust can pass this gap. But already what we see in both regions is small. So these micron-sized dust, micron-sized silicate dust, could easily pass this gap and be in the inner disk. So yeah, I have no idea currently for this.
We have a question online, if you want to unmute and ask.
Yeah, so the iron has a higher sublimation temperature than silicate dust. So at the ring position, does the temperature at the ring where you have iron and silicate separates, they kind of, the temperature is the right temperature to separate the iron and the silicate? The iron has the 1800 sublimation temperature, while silicate has 1400.
Yeah, here at this inner part, the temperatures are 1500 Kelvin. So even in this inner disk, conditions are good for silicate grains to exist. And also in this outer region at 0.6 AU, the temperature is only a few hundred Kelvin. So this is not the reason that silicates grains already sublimated, because both inside the gap and outside the gap, silicate grains can persist. But what is maybe a difference, that iron grains have a higher density, and then if there is some filtering mechanism which filters grains based on their densities, then maybe that can lead to this configuration where the more dense iron grains are can be found in the inner regions.
Thank you. Is there any other questions? Yes, go on.
So again, about the existence of iron but not silicate. So could it be because iron is more heavy, so it has a smaller blowout limit against radiation pressure?
I can imagine that this, as I mentioned, I cannot answer that question, not at this stage, but it can be investigated, although there is not quite a big difference in the densities. Like it's just two times, iron is 2 times heavier than silicates, right? And but could be, I cannot, so it should be investigated.
Okay. Is there any last questions? If not, then we can thank Jozsef again for a very nice talk.